Sir, you can start your lecture. It's now 12 participants. You can start, sir.
I mean, there's 8 participants because counting me twice, the webmaster and you. I mean, is it
Sir, I
normal that?
messaged in the WhatsApp group regarding joining of the link. Maybe within a minute or two they will join.
Yeah, but I mean, does it make sense that I just speak for? I mean, okay, maybe I don't know. I can start.
Hello,
Okay.
good afternoon, sir. May I have a
Hi.
question? May I ask a
Yes.
question? Sorry.
Yes. Of course.
Yeah, yeah. Am I audible?
You are.
Okay, sir. Actually, I have a question. Like in the last lecture, what you told about the this thing of mm, for the variables and for the factor and the variables, like for uh, how much, like how many possible values of x, uh, like the related to that, the possible values of x, there could be many more, but what is the highest number of possibility that can be achieved by optimizing all the other variables connected to that function, or we call the factor, using the all incoming input messages from all our neighboring variables. Like,
Mm-hmm.
can it be explained?
I'm not sure I understand what you mean by what's the maximum number of possibilities. Possibilities of what?
Sir, like for the each value of x, there could
Yes.
be a many various numbers of possible values for x.
Yeah.
So, what could be the highest number of achievable possibility for optimizing all the other variables that is connected to that one factor,
Yeah,
and
yeah.
using the, yeah.
Yes, yes. So, I mean, you're asking, so what's so essentially, if the variables are, let's say, discrete, so let's take a sum there, then the number of terms that you need to sum, right, is, so let's say that every variable can take only 2 value, to simplify. Then the number of terms you would have to sum over here is 2 to the power, the cardinal of xa, so number of neighbors uh, of the factor psi a minus 1, because you're summing over, you see all these xj's that are connected to the factor a, except 1. You're not summing over xi. Okay, so if instead these are integrals, if you are working in the real case, this would be an integration over r to the cardinal of this neighborhood minus 1. So this notation means the number of nodes connected to factor psi a, or the number of arguments of psi a. Is it your question? So the complexity of this integral or this sum, if it's discrete, is exponential, but only in the degree of the factor. Is it? I don't know if this is what you're asking.
I got a little bit, sir, but can you please explain this term for the neighborhood minus one?
Why is it the case?
Yeah,
What?
the nodes connected. No, yeah, exactly. This are a real of this node.
Because this factor is connected to a number of neighbors of nodes, and I want to marginalize with respect to the neighborhood of this factor, and so I should integrate with respect to all variables but one. So I'm not considering this one, and I need to integrate with respect to all the neighbors. How many neighbors there are? There is that number, and I need to remove one corresponding to this one, and so I integrate over all these configurations of the neighborhood.
Okay, sir. So this process will go in a loop, right? For each and every term of
Yes.
a tree structure, we have to ignore the other for the one set of values.
Yeah, each time you compute a message like this, you need to remove one node. Indeed, this is a marginalization operation.
Okay. Thank you, sir.
Yes. These equations are defined for every I and A, for every node and factor. So you have a set of messages of these two types, and for every node and factor. So basically you have messages like this flowing on every edges of the graph. Between every factor and node, you have a message flowing in that direction and that direction. So the total number of messages like this that you need to update is twice the number of edges that we could I could call like this of the factor graph. Okay, and you iterate these equations. Sorry, here I missed time. You iterate this equation. It's an iterative algorithm, and until convergence. Okay. Perfect. So in the notes there are references for belief propagation and all that. You can take a look. Perfect. So okay, let me just say a few words about what's the problem with this algorithm when you want to deal with these kind of structures which are fully connected graphs, and how to solve these issues. So there are multiple problems. So one of them is that there are too many messages. So like I said, the number of messages of probability distributions in the belief propagation equations that you need to iterate in this algorithm is proportional to the number of edges like this between factor and nodes. Okay, so if the graph like this is dense, meaning that essentially nodes and degrees have, or in this case only nodes have a large degree, so the number of neighbors of this node in this case is n-1. So the number of messages is of the order of n squared, because every node is receiving messages from n variables, n-1, which is essentially n, and is sending messages towards n factors, okay? And this for every node. So the total number of messages you have to update is n squared. So it doesn't look much. I mean, it's still polynomial in n, it's not exponential, but for large values of n, this becomes quickly an issue, okay? While if the graph is sparse, meaning that the average degree of nodes and factors is not dependent on n, the number of messages you have to deal with is order n. Sparse graphs. Well, this is for dense. So this quickly become a bottleneck, okay? It's not practical. Another issue is that these equations are easy to implement if these integrals are actually sums. So if you're working with continuous variables, these would be sums. I will rewrite Then in terms of sums, oops. Okay. And these are all the xj's belonging to the neighborhood of A except xi. So performing these sums is possible, okay? So again, this is okay, because doing sums like this numerically is fine. While if you have to compute integrations, even if the number of variables that you have to integrate over is 3, 4, it becomes quickly a big issue. Okay, you don't want to have to compute integrals for all of these messages. So it's not an algorithm which is very well suited for continuous variables. Written like this, it's well suited for discrete variables. Okay. Another issue is still related with this fact that you may want to apply this to inference problem where the variables are continuous. That on top of requiring to compute integrals here instead of sums, how do you encode, how do you represent these probability distributions? Because you see, if xi is a real variable, it can take, let's say, any value between 0 and 1, let's say, or between 0 and 2, whatever. You have to, this is a function, it's a probability density, okay? So how to encode efficiently in the computer a probability density if it's not parameterized in a nice way, like a Gaussian or like some known form, you cannot. The only thing you can maybe keep in memory would be an histogram of this probability distribution, which is very demanding in terms of memory. Okay, so it's hard to keep in memory generic probability distributions which do not have some specific parametric form. Okay. So all these issues make a priori this algorithm not a good candidate to perform inference with continuous random variables on dense graphs. Okay. Also because you see, if the graph is dense, here you would have an integral over r n minus 1, which is again which is as hard as the original problem. It's an integral over an exponential volume of n. You would have to marginalize with respect to all the variables but one, but given that every factor would be connected to all the others, you cannot. Okay, so you have to find some other way. So what I just said here is not an issue for the spike-Wigner model in the sense that every factor is connected to only 2 variables, okay? But if the factors were connected to many variables, in this case, you cannot do anything, okay? You can do something when variables have a dense, have a high degree, but factors still have a low degree, okay? Okay, actually, this is not true. You can also solve the issue if the factors have a high degree, but I won't talk about it. You can use, for example, this to solve regression problems and things like this. But let's focus on this spike model. So the question is, how do you simplify this algorithm? And I will not give the detail, I will just explain the idea. The thing you can realize is that if you look again at these equations, so let me write them for a generic continuous valued variable. So okay, now so let's do it for the. Let's write the BP equation for the spike-Wigner model. Wait for my notes. Yes. So if you write down these equations in this context, what you get is the following. So you just apply what I've just written, and you use it for the spike model. And so what you get is m factor ij to variable I times t xi is proportional, so up to the normalization, I'm not tracking normalizations, to the integral with respect to xj of the distribution that j sends to factor ij times the factor, and the factor is exponential minus 1/2 yij minus square root lambda over n xi xj squared. This is our Gaussian. Okay, so this is the psi ij. And that depends on our observation yij. It's our factor. Okay. While the other messages, the node to factor, is the product of all factors. So there is the factor coming from the prior. This is psi I times the product over all k. So a node is receiving information from the factors from connected to all the other nodes. So it's a product over k different than I and j of mik to I at t xi. Okay, so this is BP for the model of interest. So the key point in order to simplify the algorithm is to realize that, you see here again, because this exponent is very weakly dependent in xi xj, I can do a Taylor expansion, right? So I can do a Taylor expansion of this part, Taylor expand in 1 over square root n, thinking that n is large. Okay, 1 over, yeah. And if you do so, what you can do is compute the means ij. You can write the equations for the means and the variances of these messages instead. And the variance vi to ij So I won't do the derivation, but the main point is that, you see, because this thing is small, if you do a Taylor expansion of this exponential at second order, what you realize, so you will linearize this exponential, and then you have a quadratic term in the axis. You will so the linear term, you see, it will be just an integration of m against a term linear in xj. So it will be a function of this expectation, okay? And the second order term in the Taylor expansion of this exponential will make appear xj to the square. So you will have when you integrate with respect to m, if you give a name to the integral against such a message of x squared, and you call it v, it's like the variance of these messages, you will have these variances that will appear. And what you can show is that all the smaller order contributions, the higher order terms in 1 over square root n, they are negligible. You can forget them. So what does it mean? It means that somehow by exploiting this Taylor expansion there, the fact that these interactions between nodes are very weak, I can close the equations, so I can simplify the equations, and instead of working with these generic probability distributions, I can just work with their expectation, their mean, and their variances. And all the higher order moments do not matter. So what does it mean concretely? I'm just reparametrizing these messages in terms of Gaussians. Okay, this is the kind of central limit type of argument. So it's just the formal, like this Taylor expansion is just the formal way to show, by being able to show that any higher order terms greater than first and second moment can be neglected. You are showing that you can only parameterize. Basically, these messages are Gaussians. They're almost Gaussians, and you can discard the correction to their Gaussian behavior because parameterizing them by Gaussian is asymptotically exact. They behave like Gaussians. And now that they have, if they're Gaussian, everything becomes fine because it's easy to keep in memory a Gaussian distribution. You just need to keep the first and second moment in memory. So basically, you are reparametrizing these generic functions, which are probability densities over continuous variables, in terms of just their first and second moments. Okay, and then doing so, you can actually close the equations. You can rewrite entirely the belief propagation equations just in terms of their first and second moments. So you will obtain iterative equations on these B's and V's. The M will completely disappear. You will obtain an iterative equations that update the expectations and variances of these belief propagation messages.
So that it means instead of transmitting the M, we can transmit the message mean and variance.
Yeah, exactly.
We'll convert the whole message sequence in either by taking the mean of that equation or by taking the variance. That is a first and second order derivatives. Okay, sir.
That's the first step. Yeah, it's a Gaussian parametrization of these messages. But this is the point I'm trying to make, is that this is not just this Gaussian parametrization is exact. It's not. I mean, it's asymptotically exact. When n is large, you can show that these messages are truly Gaussian. So there is no approximation when n is sufficiently large. It's an exact relaxation. Okay, and you can just show that by doing a Taylor expansion of this kind of terms, which are very weakly dependent.
Is it possible to convert it? Or in some different cases we can convert it into this Taylor expansion into the first order or second order equation?
Different cases of what? What do you mean?
Like you have taken the case where the value of n is too large.
When n is large, yes.
Then only we can convert it into the mean and variance.
Yeah. So this Gaussian relaxation only makes sense for very large instances of the problem. But actually, in practice, so let's say you do these derivations, you obtain the final algorithm written in terms of these means and variances, so which is really a Gaussian relaxation of these messages, and you run that instead of the exact equations on an instance of your problem, which is of size, I don't know, even 500, which is not so large actually. You will see that there is almost no difference. So when I say very large, it doesn't actually need to be so large to work out this type of approximation. But what you can prove mathematically is that these relaxations are exact when n goes to infinity. Only the first and second moment matter when n is very, very large. Okay? So you can do that, and at the end you obtain another algorithm, which is just iterating these two objects, means and variances. So I will not write it. So in my notes, not the one I've shared, but at the beginning I say that there is a longer version of the notes that I've shared with you. If you click on these longer notes and you are interested to understand the details, I explain in very much details these derivations there. Okay. So that's the first step. It's going from generic probability distributions here to Gaussian distributions. So it's parameterizing this by first and second moment. So then you close the equations on this first and second moments. And the second issue that you want to solve, you want to simplify, is that still you see these moments. So you have a B and a V for every messages like this, but you have also a B hat and a V hat for every messages like this. Okay. There are still many, in the sense that now we're just dealing with numbers, which are these numbers, instead of probability distributions. We're just tracking the moments of these distributions. But there are still many such numbers, because you see they are indexed by edges. This number is indexed by an edge that go from I to factor ij, and vice versa from ij to I for the other type of message. So there are still order n squared quantities to update, and therefore equations to update in time at every iteration. This is too much. For practical problems.
This gives the high complexity in the network. Again,
yeah, it's still exactly. So it's still high. Like, from the perspective of computer science, it is not, because everything that is not exponential in n is said efficient. But for practical purposes, this is too much. What you would like is an algorithm which complexity scales as n, is linear in the number of variables. So the next step, which again I won't explain, but is again based on a Taylor expansion. But this time you can show that basically the fact that these quantities are computed without considering one of the factors. So you see, this represents the expectation of this probability distribution, where all factors are connected to node I except one. You have removed one. Okay. This is the variance here. Okay, and what you can show is that you can rewrite this quantity in terms of really the marginal means. So really, you are closing instead the equations in terms of quantities, which are the integral of mi and same for the variance. Okay. With and without a hat. So you see, it's like if in the belief propagation equations, I'm kind of forgetting that I should consider one node or one factor out in these equations. I'm trying to close the equations on really these quantities, which are the approximations of the marginals themselves. But of course, this is not correct. So, but what you can show is that nevertheless you can close the equations on these quantities, but up to a correction. So you again do a Taylor expansion if you want. You are kind of correcting for not considering the removal of a node or a factor here, and you pay a price to that, which is a first order correction, and you can compute it. So overall, at the end, you are closing equations only on quantities like this, which are indexed only by the nodes. And of course, they are related to these quantities by some corrections due to the Taylor expansions that you're doing. So maybe this looks a bit
Is it always necessary to convert a generalized model into a Gaussian model only? Why not any other parameters to follow?
I mean, you could say, okay, no, I mean, you could parameterize this distribution in other ways, but the thing is that the Gaussian parameterization is exact, because if you do really the Taylor expansion of this, you realize that only first and second moments matter, and a distribution that is only parameterized by first and second moment is a Gaussian. So if the other moments are functions of the first and second moment, they are Gaussians. And basically here this is the case. If by Taylor expansion, if you work out the things correctly, you would realize that higher moments are only function of the first and second moment. So they are Gaussians. So there is no smarter or alternative choice to do in this case.
Okay. Majorly the exponential factor also can be easily converted in a Gaussian distribution.
Yeah, if you want, it's already natural. You have already this exponential form there. But actually here this could be something else than a Gaussian if the interaction, if this factor would weakly depend on the variables, in the sense that you would have a factor like this in front which goes to 0 when n is large. Even if this would not be a Gaussian, the resulting measure would still be a Gaussian by Taylor expansion. Okay? But okay, so at the end you obtain this sorry, I need to charge my computer. Give me just 1 second. At the end, you obtain an algorithm which can be written in terms of only in terms of matrix vector multiplications, and the meaning of the quantities that you are updating is precisely this: is the mean and variances of the marginals that you're trying to approximate. The marginals you're trying to compute, for the same reason that I explained here, they are also Gaussian. And you're trying to computing the mean and the variances. And you see these Gaussian marginals that appear are precisely related to the effective denoising problem that appears in the replica formula. You remember that in the replica formula we have that the formula tells you that somehow the high dimensional problem becomes asymptotically equivalent to denoising just scalar variables, and this, okay, induces Gaussian marginals, and so the relation can be understood in terms of these Taylor expansions that I'm mentioning at the level of the cavity equation. So it's a bit difficult to say much more here in few minutes, but this is how this problem appears somehow. The derivation I'm talking about shows at the end that somehow the belief propagation equations are trying iteratively for each variable to solve a kind of denoising problem like this. It's very much connected. Okay, so I know that it's not entirely clear, and this is fine, but I think the main point here just is that we have this algorithm, belief propagation, that can be simplified for dense graphical models and be used simply by reparameterizing these messages in terms of Gaussians. Okay, and so this is really the key point. This is the hidden also central limit theorem kind of argument that I mentioned at the beginning. Okay, okay. So last remark: this algorithm comes also with a bunch of rigorous analysis. There is something called the state evolution, which is a series of theorems that precisely describe the performance of these algorithms when n goes to infinity in the large size limit. And the surprise, maybe I can just mention this to close this part. The surprise is that these theorems, at the end, so you remember this was the equation that the replica formula tells you. It tells you that this parameter Q in this formula, which represents physically the overlap, the inner product between the base optimal estimator of the signal and the signal. Okay, this is the physical meaning of this Q, because it is related to the error by this theorem. Okay, from this you can see that this Q0, which is the minimizer of this replica formula, is precisely this angle I was mentioning. So the way to find this Q is to solve this equation Q that I wrote there. Okay, it's a kind of self-consistency equation. You have Q on the left and you have Q on the right. The theorems that describe this belief propagation, or that we call approximate message passing when we use it on dense graphs, but at the end it's the same algorithm. These theorems tells you that the inner product between the estimator obtained by, so at every time this algorithm will tell you what are the means of the messages, which are an approximation for, so at convergence, the means of these messages in this algorithm are an approximation for the posterior expectation of the components. This can be a good or a bad approximation. It depends on how on the quality of the data, on the signatures row, but this is the goal. What you hope is that these things are approximations of this posterior means. The performance, the overlap between this vector of estimates and the ground truth is given by a theorem called state erosion, and it tells you that actually you can even track the performance of these things in time at every iteration. And what it tells you is that the overlap, so if you look at the inner product between these estimators and the ground truth, let me call it Q AMP for this algorithm at time t, then this Q AMP at times t, when n is large, is given by this following equation. X star plus z. Okay, so you see that it's the exact same equation and the replica formula, except that now you have time there, because you are tracking the performance of this iterative algorithm. This is the equation that describes when the problem becomes large, how the vector, your estimator obtained through this algorithm, is aligned with the ground truth X star. And it's given by the same equation. So what does it mean? It means that when the solution of this iterative equation converge to the solution of this equation, which minimize the replica formula, because you need to pick the minimizer to find the information theoretic value, the base optimal value, then this algorithm is base optimal. However, if this equation has multiple solutions, and the solution of this equation describing the algorithm, which should be initialized at t equal to 0 with 0, because at the beginning your estimator is orthogonal to the truth. If this equation converges to another solution, then the algorithm is suboptimal. And this is what allows to draw this picture. This is the region where the equation describing the performance of this algorithm converges to another solution, which is not the one given by the replica formula. In this case, it would converge to Q equal to 0, or equivalently to the error equal to 1. In this region, this iterative equation describing the performance of the algorithm, initialized from 0, meaning from no information about the signal, will converge to the same solution as the base optimal one. And so you can show that you have a base optimal efficient algorithm, which is belief propagation. Okay? Perfect. So this closes this discussion. We have a complete picture now of this phase diagram. We have understood through the replica method how to obtain the base optimal performance, through random matrix theory how to obtain the spectral PCA, and through a very shallow introduction to belief propagation, we have seen that there is a Bayesian algorithm that whose description matches what the replica formula tells you, at least in some regimes, and it gives this red curve here. Okay, so I know very well that this last lecture was very dense and fast, and I'm sorry about this. It's I wanted to spend more time on this, but now I would like to show you more applications. So if there are questions, I can answer. Otherwise, I refer to you to the detailed notes, not the ones that are that I've shared at the beginning, but if you look at the very beginning, I say at the first page that I give a link to a more extended set of notes that I've written, and you can take a look there. All the details are present. Okay, so if there are no questions, maybe I can move to the more, let's say...
Yes, any questions from the audience side?
Okay.
Do you want to ask something?
Yes, ma'am. I have a question.
Okay.
Go ahead.
Yeah. One thing what I have noticed and compared is that this method of the whole method what you have told in today's lecture and previous lectures is having the resemblance with the S matrix theory what we study in physics. Like
which theory? Say it again. The
S matrix theory.
S matrix theory. I've never heard about this. Okay, what is it?
Yeah. So actually, S matrix theory is basically about the quantum mechanical applications for the phase transitions and the particle interactions, and its comparison is done with this Spike-Winger model for the low rank signal. And particle interactions for the S matrix theory. So most of the things and algorithms, the mechanism are similar between these two things, like these two processes for the Spike-Winger model and the S matrix theory. So both of the processes tell us about the asymptotic limits and universality. Okay, so one thing what I want to infer from this and want to ask, like if someone have to do the discrete and continuous simulation for a data set, so what like for example, if I have to do a real time measurement for a data or a signal or whatever message it is so how to interpret the things if we have the different models with us, but we don't know the right efficiency and the output, like how can we get the exact and less error output from this say from the same kind of models, like how to differentiate between those things. Like one physicist, like for example, if a physicist have to interpret the data for the real-time measurement of any movement of, like for example, electrons or any particle or any data system. So how can we get to the conclusion that this model or that model is giving us the more efficient or the more accurate or less error outputs? Like how to get to that decision?
And, I think if I knew the answer, I would be probably with a lot of big prices. It's a very hard question. So your question is, for a given physical process, how can we make sure that we select the best model among a pool of candidates? Is that correct?
Yeah, right.
Yeah, I mean, I don't know in general. I mean, you can always assume different. I mean, let's say in machine learning there is an answer. So if you, I'm not entirely sure this is precisely your question, but if I interpret your question as, imagine that you have some data coming from some experiments that could be physics experiments or whatever, and you have a pool of candidates models to process this data and make inferences, how to select the best model, right?
Yeah, right. Yeah.
Yes, so there is no easy answer, but at least in machine learning there is a recipe. So in machine learning, usually, so the goal is to train a model from data to predict the output associated with an input, for example. So is to find a relation between input and outputs given examples, given data, which are of the form input and output. So this is a very generic setting. It's called supervised learning. And in this case, you may have many possible candidates models to train from the data and how to select the best one is done as follows. You should essentially train all the possible models that you have in mind. Of course, this has a computational cost, so you train as much as you can. And then you would select the one, you do what we call cross-validation. You would select the one that is able to predict the output associated with inputs that were not part of the training data. So you need to select the model that generalizes the best, that is able to fit the relation somehow on data not used for the training. This is called cross-validation, and it's a very generic approach to model selection. So I don't know if this answers your question.
Okay, yes, sir, I got it. Thank you.
Okay. Great. So let me now. Basically, this closes the course, and I would like just to spend the last 10 minutes maybe of this lecture and the last lecture to now show you let's say the broader context. Maybe I should have started with this to motivate you guys to stay focused for the course, but now I want to show a broader overview of the kind of inference learning communication problems where all these techniques that I've presented are of direct use. Okay, so just to show that I'm not lying to you, that what I've presented is really not specific to the Spike-Wigner model, but can be applied in a much broader context. Okay, so I can stop sharing here. Okay. So we have 10 minutes. I can start with this 10 minutes and then we continue after.
Sir, you have to take the last lab session also on a hands-on training? Finish.
Yeah, but we decided with Jaspal that I'm going to do this lecture instead. I wanted to show. Let's call this the hands-on part. It's the application part. Okay. That,
so by showing these applications, you will the course will be over now.
Yes, yes. So I will spend 10 minutes now to start, and the next lecture will go in. I will show more applications. Okay.
Okay, sir.
Perfect. So do you see my screen?
Yes, your screen is visible.
Okay. So the goal of my goal now is to show you that this key notion in the course, that is that of phase transition between different regimes in the problem, between different phases. So the phases we mentioned in the spike-Wigner model are the statistically impossible phase, where reconstruction of the signal is impossible, the algorithmically hard phase, where it is possible but no efficient algorithm can do so, and the algorithmically easy phase, where efficient algorithms become optimal. These kind of phase transitions actually appear in tons of contexts, which are both in data science problem, in data processing, but also beyond. So the phase transitions are essentially very universal phenomena. I'm sure that many of you know that, but I will try to show you this. So again, by phase transition, do you see my pointer?
Yes, sir.
Okay. So by phase transition, I mean again an abrupt change in the behavior of a complex system as a function of some control parameter, and this abrupt change is manifests itself in the change of some order parameter, of some observable about the system that can radically change at some value of the control parameter. Okay. So okay, let me again connect. Let's start again from the basics, because my understanding is that most of you are not physicists. So I just want to make the connection with physics even more clear. So in physics, you deal with atoms, molecules. Okay, they are very small objects, and you have tons of them. Okay, so for example, in water, in any physical system you may be interested in studying, the typical number of entities that you're describing is the Avogadro number, which is of the order of 10 to the 25, which is really a large number, which is orders of magnitude bigger than the types of numbers of scales that appear in astrophysics.
Slides are not moving. You are at the first slide. Yes, now you are at the third slide.
Yeah, I will share the screen instead. Like this. Okay. Okay, I was explaining that. Let's say in physics. Now, do you see?
Yes, we can see.
Okay. So in physics, the typical systems you're interested in are water, molecules, things like this. So they're very small objects, but you put tons of them together of the order of the Avogadro number, which are orders of magnitude bigger than the types of numbers appearing in astrophysics. This is much bigger, for example, than the number of stars in the galaxy or things like this. So these are really big numbers. And so this is a quote that I already used in the course by Philip Anderson, who got the Nobel Prize in physics. More is different, or equivalently, the whole is more than the sum of its part. So even if the molecules are the same at any temperature, and the physics that of interactions between them remain the same at any temperature, they change. They change a lot as a function of the temperature. At the global level, they behave as a solid if the temperature is small, then as a liquid, and then as a gas if you increase further the temperature. Okay, so this is what I mean by phase transition. Okay, citing Anderson, the behavior of large and complex aggregates of elementary particles is not to be understood in terms of simple extrapolations of a few particles. Instead, at each level of complexity, entirely new properties appears, and the understanding of the new behaviors require research, which I think is as fundamental in its nature as any other. So this is the starting point of this is the motto of statistical mechanics. Okay. So when physicists talk about phase diagram, it used to be only restricted to such physical systems like water. And for example, for water, the phase diagram looks like this. It tells you in which state is the water as a function of the pressure and the temperature. So here you have the liquid state in this region. Here it is an ice. So when the temperature is small and or the pressure is high, if you increase the temperature at any given pressure, at some point it will become liquid, and at some point it becomes a gas. Okay. So these are the phase transition lines between these different regions. In particular, the Earth lives there, and this is the variation of temperature. So we observe all the types of phases for water because the temperature varies. Venus lives here on the phase diagram, so all the water you find on Venus is in the gas form. In Mars, all the water is in the ice form. You are there in the phase diagram. Okay, so this picture is makes the connection with physics. So this is a kind of one-slide course on physics, but you see this is what we call the free energy in physics. This is the related to the Shannon entropy in the context of information processing systems, but so it's the way physicists describe complex systems, and the replica formula was an example of such an object. It's like a free energy, dimensional information. It tells you in which phase the system lives at a given value of a control parameter. So let's say for physical system, the order parameter would be the density of particles. So it would be, let's say by definition, 0 for liquid. It would be negative for gas, and it would be solid for positive values. Okay, so it's just a convention to set to 0 the density for liquid. And the free energy is a kind of function that tells you where the system lives, in the sense that you should select always the minimum of this free energy. Okay, so if the minimum is at the liquid state, you would observe in practice the liquid state. But at some point, if you decrease the temperature, you observe this red curve. The system, now the minimum is at the solid state. It means that the system it is more favorable from the energetic and entropic point of view to be in the solid phase. Okay, and the moment where this function has two minima at 0 temperature here, basically this is the moment where the phase transition happens, when the equilibrium becomes the solid instead of the liquid. Okay, so these are repetitions of what I said at the beginning of the course. Okay, it's okay. 11. Maybe I can just finish these slides and then we continue the next lecture. In physics, we like to describe things in terms of control parameters, which are this quantity that an experimentalist can tune, like the temperature, the pressure. And the way we describe the system at the macroscopic level are these so-called order parameters. So let's say density of particles, the magnetization in a spin system, like the Ising model that we've studied, or any other macroscopic global property of the system. In the context of inference, it would be the minimum mean square error, the overlap, things like this, the overlap with the signal. So this is really the description of the model at the large scale, not the microscopic scale. And so there are two terms that contribute in constructing the free energy in the function that I was showing before. It's a competition between two terms. One is the energy, which is essentially the cost for the system to be in the macroscopic state O, described by these order parameters. And the lower the energy, the more order there is in the system usually. So in inference, The energy, you remember, is essentially the log likelihood. So if you write down a posterior distribution in Boltzmann form, in the exponent, we recognize what we call the Hamiltonian, which is the energy, and it was the minus the log likelihood. Okay. The entropy instead is the logarithmic number of configurations corresponding to a certain macroscopic state. It's the degeneracy corresponding to a certain value of the order parameter. So, for example, in inference again, it's the number of it would be so the microscopic states in inference are all the possible values of our estimator for the unknown parameters, and the order parameter could be the minimum in square error, and basically the entropy would be the number, the logarithmic number, the volume of configurations of values of our vector that are in agreement with a certain minimum error with respect to the signal. So there are many vectors such that their square deviation with the signal is roughly the same. If you are counting them, it gives many. There are exponentially many, and the log of this is the entropy. So the higher entropy, usually the more disordered is the system. Okay, and the free energy is the difference between energy and the entropy, and the entropy is multiplied by the temperature. This is essentially a definition of the temperature. Okay, so maybe we can stop there, and what I will show you next is that this vocabulary, these notions, are really universal and can describe financial markets, imitation effects, and of course information processing systems and computer science, as I will show you. Okay, so we meet again in an hour, I guess, right? Or no? When do we meet?
Sir, approximately after 1.5 hours, exactly at 4, we'll start the next session, or after 1 hour. What you want?
I see that the schedule was supposed to
be 4:30. Yes, after 1 hour. In the written
1 hour. Okay, we meet in 1 hour then.
Okay. So all of you are again requested to join the link after 1 hour at 3:30. And thank you, sir. We'll meet you again after 1 hour. Okay.
See you in an hour.
Okay, sir.